Hello everyone. In this video, I'm going to discuss three published modeling studies related to the topic of managed aquifer recharge. The International Association of Hydrogeologists defines managed aquifer recharge as the purposeful recharge of water through aquifers for subsequent recovery or environmental benefits. And it can be accomplished by using several methods, such as surface ponding and direct injection into wells. Recharge could be from natural sources, or if it has the appropriate level of quality for recharge, treated wastewater could also be used. The intention could be to increase the amount of groundwater or to improve water quality. For example, in saline aquifers, the addition of external water could decrease salinity. Or the other reason is to store for future unforeseen scenarios such as droughts. So these are the three papers we are going to discuss. The first one is from Jordan on the Mujib Aquifer. The second is from Tunisia on the Maghnasi Basin. And the third is from India in an experimental site in the state of Haryana. So from now on, I will simply refer to the articles by the name of the places on which the studies were conducted. So the study on Mujib Aquifer was published by Al-Assad and Abdullah in 2009. The aim of this study was to determine the response, that is the distribution of heads over the basin after recharge by treated wastewater. They considered four possible future recharge scenarios with varying levels of recharge and pumping volumes. So basically, they were trying to study, for example, what will happen if 20 megameter cubes of treated wastewater is recharged within a year into the aquifer, while at the same period 50 megameter cubes of water is pumped for consumption. This diagram of the conceptual model presented in the article was a very simple representation of the aquifer. It is good to have such a simplified representation because it makes the modeling problem clearer. There are two aquifers separated by an aquitard. The upper aquifer is partially overlaid by a dry layer, but since the water level in this aquifer is below the bottom of the top layer, they considered it an unconfined aquifer. Although there are fractures in the calcification, they modeled it as homogeneous, and this is the layer the study deals with. It has a thickness in the range of 100 to 300 meter, and it has outcrops in the west and central parts of the basin. So these are potential locations for recharge. And the surrounding mountains were modeled as constant head boundaries. The river, which is locally called Wadi, and it is connected to the aquifers through underground caves, and the surrounding desert were modeled as constant head outflow boundaries. They justified this by mentioning that the abstraction wells are far enough from the boundaries, but numerical arguments should have been provided. This second article by Cianini and Mamu aimed to evaluate the effectiveness of recharge and to select zones for recharge by combining GIS and numerical modeling. The data collection was aided by GIS and field data from bore logs and pumping tests and other related data. Model represented a multi-layer aquifer with 3 layers. The major weakness of this study was concerning boundary conditions. They say that boundary conditions were assumed in the first step and then tested. So it seems that boundary conditions are additional parameters to be calibrated. But I think this worsens the accuracy by adding to the existing uncertainty of the overall model. This study, published in 2009 by Goyal et al., unlike the other studies, was conducted on an experimental site, and it was a local model. The aim was to test the effectiveness of a finite element model in simulating recharge in a cavity type well, where water enters from the bottom. The model is called HydroStudy, and it is good at simulating variably saturated flow. It uses Richard's equation, which is the unsaturated analog of Darcy's equation, Unlike Darcy's equation, which relates the variation of air in space with respect to its variation in time, this one is stated in terms of the variation of water content with respect to time. And the hydraulic conductivity is also the function of the variable water content. And it is a difficult problem to solve numerically due to numerical convergence issues. When we come to the conceptual model, it is not clearly stated, but we can infer that they are modeling a multi-layered cylindrical soil mass of 500-meter radius with a depth of 69 meters. It is modeled as an unconfined aquifer with no flow boundaries on all sides, though they didn't explain the reason for assuming no flow boundaries and whether it has anything to do with the radius of influence of the pumping and injection operation. So now let's move on to their modeling methodology. The first two studies used ModFlow, while the first study did not specify whether they used a graphical user interface or a command line program. The second one used the PMWin graphical user interface to work with ModFlow. The third study, as I have mentioned above, used the finite element model Hydros 2D. This makes sense as the third model, unlike the first two, assumed variably saturated flow in their conceptual model. And Hydros 2D is ideal in modeling such cases. The first two are regional models as they cover a large area, but the third one could be categorized as a local model because it is trying to simulate the area around a single well. Though they did not explicitly state it, the first two were 2D aerial models, which use the Dupuit-Forkheimer approximation, where flow is assumed to be horizontal and vertical hydraulic gradients are negligible. So the grids run in the two horizontal directions, whereas the third model is a profile model where a vertical section cuts through the soil, and the volume around the well is modeled as axially symmetric. The first models used both transient and steady modeling, while the second was steady and the third is transient. This depends on the particular objectives of the study, of course. So, for example, in the second study, it was not important to capture what happens during the time of recharge because they were considering the long-term effects of recharge, and so they used a steady model. The grid geometry of the first study was irregular with a grid spacing of up to 4,000 meters, while the second one used regular grids with 500 by 500 meter spacing and on 3 layers. This large grid spacing could be explained by the fact that they are regional models and so they cover large areas. The third one, even if they used a software generated mesh, they should have at least mentioned mesh density. Soil hydraulic parameters were mostly derived using previous studies, pumping tests, and measurements of undisturbed samples. And then they used these parameters in the first runs of their calibrations. The steady-state models employed manual calibration, though this is not a good practice. The calibrated variables were hydraulic conductivity and recharge rate. They were calibrated against existing observed head data, where the aim was to minimize the residual error of the heads. To gauge the fit of the calibration, the first one used multiple statistical measures such as the mean average error and the coefficient of determination, but the second one only used variance, and this is not adequate. In the transient calibration, the first one used the same methods as in the steady-state model, and the only difference in this case is the calibrated variable was specific yield, and the third study used automatic calibration, and the variable was saturated hydraulic conductivity, which was later used in the validation phase. Now let's move on to the criticism of the studies. In the Mujib Basin study, they used part of the data for calibration, and the rest was used for validation. As stated in Anderson and Wozner chapter 1, this is not a good practice as there are a lot of parameters in hydrogeological models, and to provide enough constraint, all the data should be used for calibration. And they mentioned that data from 12 wells were used for calibration, but they did not show their distribution in the watershed. This should be useful to judge whether the model is biased due to possible concentration of wells only in some locations. For the McNasty-Bayesian study, like the previous one, they should have used multiple statistical parameters because a single parameter like variance is not enough to judge the accuracy of the fit. They used topographical arguments to judge the accuracy of fit, but this is not a good practice as small extrapolation errors will lead to significant errors in recharge and discharge calculations. In the third study in modeling flow to wells, which is a local problem, it is better to use 3D models as there might be components of flow in the tangential direction. They should have also explained why they used no flow boundaries at all phases of their cylindrical model. They should point out if it is related to the radius of influence of pumping action or something else. As a general issue with all the three studies, they struggle with framing the problem correctly. Sometimes it is hard to tell whether they are talking about forecasting or handcasting. We have also seen two of the models using manual calibration. This is not recommended as it is time-consuming and prone to human judgment errors. And it is also difficult to find out which parameters are the most sensitive and therefore selected for calibration. The other thing is regarding communication. In science, communication is as important as the technical work because scientific experiments by principle need to be replicable, and this is not possible without effective communication. And calibration procedures should have been explained clearly, and their text is difficult to read because of poor explanation, repetition, and grammatical mistakes. The quality of their pictures should also be improved. So, what are the lessons learned in reading these three studies? The first is that numerical modeling can be effectively used to simulate recharge scenarios, to select recharge locations in both transient and steady conditions. And boundary conditions are hard to determine in regional models by inspection. So GIS should be used intensively. Two-dimensional aerial models can be effectively used to study large basins if the appropriate level of simplification is warranted. That is, if the aquifer can be modeled as horizontally homogeneous and we don't have any significant effect from abstraction wells or other source and sink features. Furthermore, when modeling variably saturated flow, there are models which are particularly effective in this domain, such as hydrostudy, and we should always look for alternatives in modeling wells and other inherently 3D problems. It is recommended to use 3D models, but there might be flow components in more than one direction, and a properly calibrated model can be used as an input to future studies by providing simulated heads data as an input to other models. Finally, this is the full reference of the discussed studies. These are the references I used during the study, and thank you for listening.